Good morning. So I have to play with two. Okay, so I will play with that too. So I'm supposed to do it, yeah. So I will present this morning some testing that we have performed on the 65 nanometer PLL coming from ST Microelectronics, okay. This is a test vehicle, basically, so you will see that inside this ASIC between card or vehicle, you will have a bunch of different, I would say, libraries. Okay. This has been done in cooperation with the CNES, Florence Malou, of course, people from STM and the CRO, basically Wafer Fab, and people from IREX, which are part of Altair Technology. So, really quick advertise around, I would say, so Altair Technology is part of the TÜV Nord division. Okay, so we have 6 divisions. We got 1 division for energy, 1 division for IT, 1 division for mobility, which is the car certifications, okay, health and nutrition, natural resources, which is mining basically, and our division, which is aerospace and aeronautical. Okay. So if I jump on that one, so Altair Technology, it's 30 years of life, okay. You have several brands under Altair Technology, so you got Altair, of course, IREX Engineering, so Altair 2 sites, Madrid and Sevilla, IREX in Toulouse, very close from the CNES, Toprel in Italy, and we just made the acquisition of an assembly company called Optocap, which is in Scotland, mainly focused on optoelectronics, but also on plastic package and so on. So we are very proud of having Optocap on board as well. If I jump to IREX, Toulouse, real focus. So we have been acquired in June 2011 by TÜV Nord. In IREX Engineering, we are 50 employees, it depends time to time, okay. We got a facility of 800 square meters, all the certification stuff, basically. And if you take a look, the main population is engineers, PhD, and we have also technicians, okay. So let's jump on the silicon stuff. So this 65 nanometer test vehicle, it's based on the standard STM libraries, okay? Except that they adapt a little bit and work around, I would say, the standard libraries. So what you will find here in this library, it's basically standard memories compilers, call sparing stuff, and PLLs, okay? The test chips or the vehicle that we are working on was a code name called Piratval. This vehicle, it's based on the, so you will find inside 2 radar PLL, so 1 radar PLL which is there. You got the standard PLL here, and as you can see, some work has been performed around the radar PLL in order to ensure that you got good immunity to radiations. Here you got basically the 2 outputs of the PLLs, and then you have a bunch of IOs, okay? So the IOs are defined here. You got some bidirectional IOs with different voltage, I2C IOs, and LVDS IOs as well, okay? Plus, in fact, the call sparing, which is very important for our business in space, as we want to have some backup in case of any issues. So if I jump now in the PLL itself, okay? So this PLL, as you can see, STM has worked on several things in order to improve it, okay? First thing, we got this morning a question around metallizations. So we got 7 layers of copper metallizations with low-K intermetal dielectrics. Transistors have been working, so you got DPNOL transistor implementations in order to be immunity for the lecture sensitivity, basically. The PLL itself is based on the charge pump type, which is just in the middle, I would say, of the design. Supply voltages, 1.2 volts, very low, okay. You got some digital lock detections, which are there, okay. So you got one which is a fine locked structure, and the coarse lock structure, okay, so 2 different detectors. As you can see, you got 6 different outputs on the PLL. So basically you got all the basic functions here in order to be able to develop later on some products. Okay. Very important also the VCO, so 200 megahertz up to 1.2 gigahertz, which is big, I would say, frequency range. Operating supply as low as 1.8 volts, 0.8 volts, sorry, and 1.32 volts. And temperature range minus 40 degrees C, and we have tested at minus 55 degrees C, so it's compliant with the space stuff. So, what was, I would say, the difficulties when you take a look at this such kind of devices? Okay, so imagine that we got a dynamic bias. Okay, so the PLL was working during the radiation. So everybody enter into a source, a total dose source, and you know that at least you have 10 meters from, I would say, the biasing stuff up to the components. Okay, so that's point number one. First difficulties. Okay. Second difficulties, you see that the IOs, you have a bunch of IOs, you have I2C, bidirectional IO, LVDS IO, standard PLL IOs, and so on. Okay. Each IOs got different voltages. Okay. So one point that was very key, okay, was to monitor all the voltages at the same time during irradiation. Okay. So the sampling that we got 2 times 22 devices coming from different lots, okay? So in total means that you got 84 supplies to monitor at the same time simultaneously during the radiation, which is quite a lot, okay? So here you have some figures. First of all, the cabling you have and the wiring, you have to be careful about that, okay? You see here the trays with the devices on them, okay? And this is the system that we have used, which is the build system, which enabled us to monitor continuously the power supplies during the radiation. As I mentioned initially, we have been able to force to put some buffers in order to send the clock permanently to the PLL and be able to acquire the results on time. Just to give you a brief idea, okay, it's a big table, okay. What you see here, it's different groups of devices, okay. So we have 2 times 11 parts, okay. And here, this is all the power supplies, okay. So some power supplies were monitored individually, okay. Some power supplies we group them because we got enough resolutions in order to ensure that I would say we detect any failures. So big challenge there. So test campaign. We performed 2 test campaigns. One test campaign was dedicated really to the PLL. Okay, we want to characterize the PLL, and we would like to see how the PLLs react with the total dose. Okay, so which is basically this table. So as you can see, there are some power consumptions and so on. Okay, but really we focus on the PLL with all the jitter measurements and all, I would say, the bit error rate. All the analysis that you can perform, I would say, on the PLL, and I will come back on a minute on that. The second TID campaign, we focus on the IOs. So we take a look at the capability of the LVDS, the I2C, the PLL IOs, and the bidirectional IOs. Okay. So this is the type of setup that you will have. We use a tester from Credence, which is a digital tester. We add some analog stuff around it. And if you want to perform a jitter measurement, you need to have a signal digital analyzer, okay, which is an SDA from LeCroy, basically. Now, the 2 difficulties, initially we think that we will be able to manage one single board to perform the PLL measurements as well as the IO measurements. Forget about that, okay. If you want to have enough resolutions and enough, I would say, performance on your measurement, we decided to split, okay. So we dedicated one board, which was very dedicated to all the PLL measurements, and we dedicated one board to perform all the IOS measurements. Okay. So just come back 1 minute to the PLL in order for the next slides to understand. Okay. When we talk about jitter on the PLL, you have several jitters. Okay. You got the bounded jitters and you got the unbounded jitters. Okay. In the bounded jitters, you got already two types of jitters. You got the jitters that incorporate all the noise by itself, by the devices, okay, which is the correlated jitter. And then you have the uncorrelated jitter, which is your environment, which is bring back all the noise, okay, so your power supply, your cable, your wiring, and so on, okay. if you want to perform a real analysis and be able to compare apple to apple, you have to perform the two measurements, okay? And then you can compare the data. Otherwise, it doesn't make sense. You will send back some information which will incorporate both noise due to the PLL itself and noise due to the environment itself. Okay. So let's go to the charts and really quick see the results that we got. Okay. So I will explain one chart. So we perform the radiation up to 300K rad. Okay. So the first portion here, it's all the steps that we have performed during the radiations, intermediate steps, okay? Then you got the 24 hours annealing, and then you got the 168 hours annealing, okay? The blue line at the top, you cannot see that really, but the blue type at the top are the limits that have been set, okay? So this left-hand side, that's the results for the radar PLL. The right-hand side is the results for the standard PLL. Okay? So if you compare now the two results, so first of all, across the radiations, so at the top you got the PLL log time. Okay? As you can see, I mean, completely not sensitive at all to the radiations. Same for the jitters, okay, and same for the periodic jitter. Okay, so pretty well and pretty good, I would say, cheap. And when you compare that with the standard PLL, you see that you have similar results, except that the figures are a little bit higher here due to electronics that incorporate at the PLL radar level. The IOs. So the IOs, you got the VOH, VOL, you got the VOS for the LVDS, okay. The differential voltage, the VTH, the threshold basically. You got the propagation time, low to high and high to low. As you can see, it's encephalogram flat. Okay, no issue at all. I mean, well in the limits. You got the VOD here, the VTL. So I mean, and we also measure the skew, which was very difficult to measure. You don't see the figures, but it's a few picoseconds. Sorry. And as you can see, I mean, the skew, there is no difference across the different IOs. The bidirectional, same thing. Okay, so pretty good results on the bidirectional IOs. So same type of measurements. You got the VOH, VOL, you got the propagation delay here, VIL, VIH, and the hysteresis, basically. I2C, same, okay, so pretty good results. Cold sparing. So cold sparing, we are looking for cold sparing in case of redundancy, okay, so basically we shut down the devices during the space mission, and if we need to start it again, we want to ensure that the other parts around doesn't affect with cold sparing stuff, okay. So for electronic people, the cold sparing, if we want to measure that, it's leakage current. And especially it's what we call IOZ, leakage current measurements. Okay. So here you have got the results. So basically what we have done is that we ensure that we got a 1 megohm resistance impedance on the IO. So during the radiation, we don't do anything to the IOs, and then during the test, we shut down the devices, stress the test with a voltage, okay, measure back the leakage current and see how the device reacts. Pretty good result as well. You got a few samples going up, but the limit was 100 nanoamp, and we are around less than 40 nanoamp. So pretty good results. So conclusions. Remember, initially we got performed the measurements on 2 different lots. Okay, so the first idea was to measure if we got dispersion in the wafer fab in order to ensure that we don't have that. We measure 2 different lots, and as you can see on the figures, there's no much dispersion in the 2 different devices. No functional failure at all, okay, which was pretty good. The cold sparing was, I would say, as I present, also positive results. And very important, it can operate up to 2.5 volts and 600 megabit per second, which is pretty high for this kind of PLL. Log time, you see the difference for irradiation. Initially we start with 38 microseconds. We finish as 37 microseconds at 300 kilorad, so no dispersion bad. For the jitter, same type of things. We start at 306 picoseconds and we finish at 322 picoseconds, which is peanuts in terms of results. The PLL radar is fully immune to the TID. This is a conclusion, definitively. Okay. And that's it.